Hey everyone, and welcome back to the channel. Today we're diving into a topic that's incredibly important, especially for those of us living in coastal areas, assessing how well our local infrastructure can stand up to a tsunami. It sounds like a huge task, right? But by breaking it down, we can understand the risks and the science behind building a more resilient community. First things first, what exactly are we talking about when we say infrastructure? It's not just the big, obvious stuff like bridges and skyscrapers. We're talking about the entire network that keeps our communities running. This includes critical facilities like hospitals, fire stations, and police headquarters. It also covers our utility systems, the power grid that lights our homes, the water treatment plants that provide clean drinking water, and the communication networks that keep us connected. And of course, it includes our transportation systems, roads, railways, ports, and airports. All of these are vital, and if one part fails, it can create a massive domino effect. So how do we even begin to assess the resilience of all this? The first step is to understand the threat itself. Scientists use sophisticated modeling to predict how a tsunami might behave in a specific location. They look at factors like the shape of the seafloor, the topography of the coastline, and historical data from past tsunamis. This creates what's called an inundation map, which shows which areas are likely to be flooded and to what depth. This map is our foundational tool. It tells us which pieces of infrastructure are sitting in the most vulnerable spots. A hospital located in a predicted high inundation zone is obviously a major concern. Once we know which areas are at risk, we can start looking at the structures themselves. This is where engineering and material science come into play. We need to ask, what are these buildings made of? How were they designed? Modern building codes in tsunami-prone regions often require specific design features. For example, you might see buildings with soft stories on the ground floor. These are open spaces with reinforced columns designed to let water pass through, reducing the immense force exerted on the structure. Another key design is the use of deep foundations and strong, ductile materials, like reinforced concrete or steel that can bend without breaking. We assess whether existing buildings, especially older ones, meet these modern standards. We also have to think about something called structural loading. A tsunami isn't just a big wave, it's a powerful debris-filled surge. The force it exerts is immense. Engineers calculate both hydrostatic forces, the pressure of the standing water, and hydrodynamic forces, which is the impact of the moving water and the debris it carries, like cars, trees, and even parts of other buildings. So, a resilient structure must be able to withstand not just being submerged but also being hit by a battering ram of water and debris. We assess if a building's columns, walls, and foundations are designed to handle these specific types of forces. Beyond individual buildings, we need to look at the network as a whole. Let's take transportation. A resilient road network isn't just about having strong bridges. It's about redundancy. Are there multiple evacuation routes leading to higher ground? If one bridge collapses or a road gets blocked, is there an alternative path? Planners use network analysis to identify critical bottlenecks and single points of failure. The same principle applies to our power grid and water systems. Are there backup power generators for critical facilities like hospitals? Are water pipelines protected from being severed or contaminated? A resilient system is one that can continue to function, even if parts of it are damaged. Another critical aspect is the location and protection of what we call lifeline systems. Think about power substations or water treatment plants. Often these facilities can't just be moved to higher ground. In those cases, engineers design protective measures. This might involve building strong seawalls or berms specifically to shield that facility. We also see innovation in making the equipment itself more resilient. For example, sealing sensitive electrical components in waterproof enclosures or elevating them above the predicted flood level. Assessing the protection level of these lifelines is a key part of the overall evaluation. Let's not forget about our ports and harbors. They are, by definition, right on the water's edge and are economically vital. Assessing their resilience involves looking at the strength of piers and breakwaters. Can they withstand the powerful currents and surges? How quickly can the port be cleared of debris and become operational again after an event? This is crucial for getting aid and supplies into an affected area. Modern port designs often include features that minimize damage and speed up recovery. So, when we put it all together, assessing tsunami resilience is a multi-disciplinary effort. It combines geology and oceanography to predict the hazard, civil engineering and material science to evaluate the structures, and urban planning and systems analysis to look at the entire network. It is about asking a series of critical questions. What's in the path of the water? Can it withstand the force? Is there a backup plan if it fails? Understanding these principles allows us to see our own communities with new eyes. You can start to notice things yourself. Are the main roads to higher ground wide and clear? Are the hospitals and schools located in safe zones? Is there evidence of protective structures along the coast? By learning about this science, we are all better equipped to be part of the conversation and advocate for safer, more resilient communities. It's a fascinating field where science directly translates into saving lives and protecting our way of life. Thanks so much for watching today. I hope this gave you a clearer picture of what it takes to prepare our infrastructure for a tsunami. If you found this interesting, please hit that like button, and don't forget to subscribe for more deep dives into the world of science and engineering. Stay curious, and I'll see you in the next video.